in your Algebra 2 honors class or whatever, I always show you guys the same strategy as far as setting up and solving these problems. In your book, they write everything out horizontally, going left to right. Doing math, whether it's adding and subtracting horizontally, is a big giant pain in the butt. So, here's what I did. You guys were all taught how to add vertically. You were all taught how to subtract vertically. Whenever you have a problem like this, automatically rewrite it in descending order, lined up with the variables and their with the correct variables in the same spot, and do everything vertically. 6-3.
No, I meant like once we set it up.
Yeah, then it's just a matter of adding and multiplying, then you're using those same properties. So when I set this one up, I start with the first one. So I have 3x cubed plus 2x squared minus x minus 7. Notice in that problem, it has a descending order from it's a third degree polynomial. There are 4 terms. I don't have to worry about any placeholders. Do you agree?
I do.
And the other one I'm adding, so all I got to do is just line them up. X cubed minus 10x squared plus 8. What goes in that hole there? 0x plus 0x. Now, the first couple times I show this, you'll probably get the idea of it and you don't really need to worry about it as much. Now remember, all I'm doing here is I'm adding everything. What's 3 and 1? Now here's the idea. Is this going to be 4x to the 6th or 4x cubed?
4x cubed.
Good. Good, good, good. When you're adding your exponents, don't change. It's combining like terms, ladies and gentlemen. It's just combining like terms. Same thing, 2 and negative 10. You get negative 8. Negative 1 and 0. Negative 7 and 8. Yay! Happy math. You have to worry about your rules. Your exponent rules. Okay. What do you think the scary part's going to be of adding and subtracting? Signs of subtracting. Let me show you an example. When you're working with subtraction, you set it up the exact same way. Sorry, my handwriting was pretty crummy there. I have 5x squared plus x. We're going to put them in that vertical order again. So it's 5x squared plus x minus 7. Notice again, I have a descending order, x squared, x, and a constant. No big deal, no placeholders. From that, I'm going to subtract 3x squared, negative 6x, and negative 1. So I just write it below, 3x squared minus 6x minus 1. And I'm subtracting each one of these parts. Most people will just forget it, and they'll only subtract the first one. By rewriting vertically, it forces you to see each problem, 5 minus 3, 1 minus negative 6, negative 1 minus negative 1. Put that subtraction symbol in between each one of them, so you're basically breaking it down into what's 5 minus 3. What's 1 minus negative 6? What?
What? No, it's 7, silly goose.
Negative 7 minus negative 1. Negative 6. And all I'm doing is put my variables with it. This was positive, and there's that. And that's it. All you have to be careful with here is subtracting negatives. By splitting it into multiple problems, you're just looking at each one every time. That's why I write things up vertically, and I try not to do any other nasty stuff. Adding and subtracting horizontally like that is just a big old pain. It's too easy to miss a sign. By just taking the problem, when you're reading it in your books can write them all out horizontally. When you write the problem down, just automatically write it vertically, and you're going to get it right every time, unless you do something silly here. Okay? Does that make sense? I know we've all done this, right? Maybe. I hope. Or at least if you did, you might not have slept through it. All right. Well, since I know that you don't like the subtraction ones, take a second. Do this one. Try that one, please. Did you guys all catch the placeholders?
Yeah.
Yes, placeholder. Remember, the biggest trick here is if you start with the fourth degree, you're going to have 5 total terms. Yes, sir. What's that? Negative 12 minus negative 12 is negative 12 plus positive 12. Same change opposite. If you want. There's many ways. There's plenty of ways of doing it. I always just write it up this way. I think it's just I'm very old-fashioned when it comes to your basic arithmetic operational stuff. I like to do just the same method every time. I know that there are tons and tons and tons of different shortcuts and things out there, but I try to show the most basic method that most of you guys have seen throughout your lives and just let you work with it. I'm not going to say this one way is better than another. It's just habit. That's all it is. Okay? And like you guys said, the tricky part's going to be, it's really fuzzy, is when you have to do multiplication now. What's going to happen when you're working with multiplication is that what do you have to remember to work with? Yeah, you have to worry about all of your exponent rules, the stuff that we did that was in 6.1. Remember that little chart that was on page that had all the same base, different exponents you add, things like that, okay? Or it's the thing right behind you on the wall. So if you had not already written that down in your notes, that might be a good idea. Or better yet, go take a picture of it. It'll be on your phone, which is your phone is next to you while you're doing your homework, and you don't have to go back and forth. It's crazy technology, isn't it? So remember, in this instance here, again, it's nothing more than distributive property and then combining like terms. Quick jump, take a picture and get in front of it and say, yay. When you're multiplying through, like I said, it's distributive property a couple of times. X times 3x squared is how much? X times negative 2x. X times negative 4. And then send the other one, negative 3, to all three of them. So you get negative 9x squared, positive 6x, and positive 12. From that, the last thing you have to do is just combine your like terms. Okay? Combine your like terms, and remember, I want you guys to always stay consistent by putting everything in that descending order. Remember, that means you're starting with the highest degree and working your way on down. So you have 3x cubed minus 11x squared plus 2x plus 12. Okay? What's the degree of that polynomial? The third degree, right? How many possible zeros do you think there are?
2.
What's the degree of that polynomial? How many possible zeros could there be? 3 of them. How many times would it cross the x-axis then? Possibly. 3.
Why?
Because we're getting there. We're starting to plant the seed of things to look for. Remember when I talked about last chapter when he said, is that a maximum or a minimum? And I eventually explained what that meant. You'll start hearing me ask these questions again. I won't tell you that. But that's kind of the same idea. I try to give you guys vocabulary as we're going through. Does it matter which direction you FOIL?
No.
Does multiply, or the order of multiplication, does that matter? Would it be easier to distribute 3 times going this way or just going this way?
2.
It doesn't make a big difference at all. I'm trying to think if there's a really difficult problem. There really isn't. Oh no! This looks very frightening.
Goodness.
It is.
No, not the 3 numbers
So-
in a sentence.
Let's take a scary look at the one up on top here. I have 3 things to multiply. It's frightening. Don't worry. It's okay. We'll get through this together. Once again, it does not matter the order in which you multiply these things together. So what I would do, since you're looking at multiplying 3 binomials together, FOIL 2 of them and then distribute the third. Once again, what I mean is I'm just going to FOIL those 2. X squared plus 3x minus x minus 3. So I have x squared plus 2x minus 3. And then to that, I multiply the x minus 2. There's no particular order in which you have to do that. You're going to get the exact same result. But what I'm saying here is that break it down in an easier problem. There's no reason to sit there and distribute out. It's just a big pain. FOIL 2 of them, and then distribute the third. And you'll get the same answer. Does that make sense? So when I FOIL that out, we get x, or excuse me, when I distribute out, x cubed plus 2x squared minus 3x minus 2x squared minus 4x plus 6, otherwise known as x cubed minus 7x plus 6. Ooh, can I ask you a fancy question? If this was set equal to 0,
And a
what are the zeros?
-3, positive 1, and -2.
2, 1, and negative 3? Okay. So it crosses the axis at 1, 2, and negative 3. What's the value of A? What's the leading term coefficient? 1. It's an x cubed, so the value in front of the x cubed is 1. Is that positive or negative?
Positive.
Is this increasing or decreasing? Increasing. It's increasing because the first term is positive. When I say a function is increasing, that means it's going from left to right, it's going up. But in order for it to have 3 zeros, it means it has to have a change in direction somewhere. So it means if it's going up, it's got to come down, and then it's got to go back up. Crazy, isn't it?
So, like, if you had one of those things with, like 100, like, here's a number, would
Yeah.
cross it like 100 times?
In theory, yes. If they're imaginary or real, if we had real solutions, yes. What we're doing is building polynomials. We're going to be getting to this. Now, remember when I gave you a definition yesterday? Bless you. What was that called? Local maximum. Not exact maximum, it's a local maximum. It's a local maximum within these parameters. And therefore, this would be the local minimum. The calculator would have been able to figure that out by pressing a few buttons, right? We're getting to that. We're not doing this straight out today, but we're getting there. All right? Questions? Are you guys okay? Yes, sir.
Where'd you get the?
Which points? These?
Yeah.
Oh, yesterday when we talked about where things change direction within these polynomial graphs, what happens here is that when we had just a regular old parabola, that value was the lowest point of the entire function. That was the minimum. When we get into the upper degree graphs and polynomial stuff, you could have many different upper levels and lower levels. What happens here is that you're looking at a specific chunk of the graph, and this specific chunk of the graph in this local area, that's the local maximum. That is the highest point within the parameter.
How do you know it's like that?
When you put the polynomial in your graphing calculator, you'll see the curve.
You can't get it from the equation.
Not necessarily yet.
Okay.
We'll get there. What I'm trying to do is get you guys accustomed to the vocabulary before we get to start to see it more and more and more. And that's all I'm getting at right now. Okay? One of the other things, there are also shortcuts. This is right out of your book. I have been told over and over again by Mr. Thames that if I do not show this to you guys, he's going to beat me up. He's going to take my lunch money. And he's going to steal my dog.
Give him the cat. No one likes cats.
I do.
Yeah,
I want to remind you guys of something here. I want to remind you guys of something. A plus B quantity squared is another thing of saying junk squared, right? Junk squared means what? Junk times junk. He hates the fact that I show it like this. I write it out like that. You know why I keep saying that? Because so many times people see this, x minus 2 quantity squared, and you know what they write? You sure? Ladies and gentlemen, one of the biggest mistakes you guys will always make is that you see junk squared and you distribute it in. The distributing in part only works if it was A times B quantity squared. A plus B, it's junk times junk. So raise your hand and repeat after me. I solemnly swear when I see junk squared, I will do junk times junk. Otherwise, Mr. Thames will beat Mr. Murphy up. Yeah, I see everybody's like, oh, wait, no. Seriously, in all honesty, I have you on recording that you were never going to do this. Evidence! Except for you two weren't talking and I just saw the high five. I joke, I kid, but seriously, this is one of the biggest mistakes most students will make. Just be careful, watch through it. Also, within here there are some special patterns. There are some special patterns for cubing binomials. It's junk cubed. Remember, that's junk times junk times junk. So, do you need to memorize this special pattern? You don't, because you can do junk squared and then distribute the third term. This is just a shortcut. Is it the end-all, be-all if you memorize it? It's not that big of a deal. I never remember it. I'd always have to go back and look it up. I always do junk squared and then distribute in again. Okay? Just remember, when you see junk squared, it's junk times junk, and everybody will get along. All right. Let's do on page. Let's steal your book, please. There's a lot of stuff here. I got
like so many people.
6-3, let's see.
So I wanted to see that in the theaters.
Page 341. What is that? 22, 24, 26,
Seems like
38,
we're
40,
even.
42, 50, 52, 56. It's 9 problems. Can we get 9 problems done? I know. I wish you luck.
My gosh.
All right?
The end of stuff? I got stuff.
That's great. It starts with an earthquake, bird, snakes, and airplanes. Lenny Bruce is not running either.